I'm Anil Kumar. As you know, trigonometry is a very important part of calculus. But by the time we start calculus, we have really forgotten most of the concepts or even the formulas which we learned in trigonometry. So I hope it is a good time now to review and recall what we learn about trigonometric functions. So in this particular video, I am going to touch upon few concepts. We'll talk about relation of trigonometric ratios, radian measurements. So when we talk about calculus, all the calculations have to be done in radians. Remember that, right? Then we'll see what is period, amplitude, and phase. We'll solve simple equations, compound angle formula. We'll work in details, derive double and half angle formulas, take up few trigonometric identities, and solve few trigonometric equations. So that will give you a brush up and help you understand how to do calculus, derivatives, applications on rate of change and optimization. So you need all these concepts, right? So let's take them one by one. On this page, we have some space. So let me touch upon the trigonometric ratios. So basically, trigonometric ratios are sine. We take angle as theta, cos theta, tan theta. So these are your primary trigonometric ratios, and reciprocal of these, which we say are 1 over sine theta is 1 over, we can write this as cosecant theta, 1 over cos, we can write 1 over secant, right, the reverse way, and tan, 1 over cotangent theta is tan theta. So purposely I've written it on the other way. You normally write cot theta as 1 over tan theta, but it's either way same thing, right? Now these are your trigonometric ratios. On xy plane, if I consider this as my xy plane and take up a point anywhere on this plane, let me take in quadrant 1 for the time being. Let's say the point is P, whose coordinates are x and y, and P is r units away from origin. In that case, what is sine theta? If this is the angle theta, then when we drop a perpendicular from P to x axis, this value is y and the x value is this, right? So here we could write all our ratios as sine theta is y over r, cos theta is x over r, tan theta is y over x. To remember all these things, we have been using an acronym which we say SOHCAHTOA. Let me write here. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tan is opposite over opposite over adjacent side, right? So that is tan. Correct. Now these are the reciprocal ratios. Now you'll also recall that in any triangle, let me make a triangle here, a big one. Let's say that's the triangle. When we say that this particular angle here is, let's say, theta, then what is the other angle? Well, the other angle is 90 minus theta if we are talking about a right triangle. Perfect. Now, if I have, let's say this side is, this is y, this is x, and this is r, you will recall that in this particular triangle, as we see, sine theta is y over r, cos theta is x over r, tan theta is y over x. What is sine 90 minus theta? So we are talking about degrees for the time being. Then you have to look from the side which has angle 90 minus theta. So the opposite side is this one, right? So if that is the opposite side, then sine 90 minus theta will be x over r. You can see x over r is cos theta, so I could write this as cos theta. Do you see that? Similarly, if I want to write what is cos of 90 degrees minus theta, cos of 90 minus theta is y over r, which is sine theta, right? So that gives us co-function identities, right? So what we just derived here is called co-function identity. Correct? And if we continue and say tan 90 minus theta, you'll find this is equal to y, x over y, right? So it is x over y. It is reverse of tan theta. It is cotangent theta. Do you see that? So these are the co-function identities which we had been working with. Another important thing to remember is that in our coordinate plane, we have 4 quadrants, correct? This is quadrant 1, this is 2, 3, and 4. Now in the first quadrant, all are positive. In the first quadrant, all are positive. So we write A, all are positive. Here sine is positive. In third quadrant, tan is positive. In fourth, it is cosine, which is positive. So that gives you an overall picture of our relations of trigonometric ratios. And remember one thing, now when we talk about calculus, all the calculations will be done in radians. We are going to discuss that also in details. So let's move on and see some other relations of trigonometric ratios. So we'll talk about now the Pythagorean identities. So we now know, we have recalled that in any quadrant, if there is a point P represented as xy, in that case, let's say this is the point P, which is given by the coordinates x and y, where x is horizontal distance, y is vertical distance, and theta is the angle, r is this side. In that case, we know that r is equals to square root of x square plus y square. Correct? We could also write this as x square plus y square equals to r square. Now if I divide all these terms by r square, what do I get? I get x square plus y square equals to r square. Dividing by r square, all these three terms, we get x over r. Now x over r is cos theta, right? So this gives you cos square theta, y over r is sine square theta, and r over r is 1. So we get one very important relation, which is cos square theta plus sine square theta is 1. Now this is Pythagorean trigonometric identity, correct? You can always rearrange this and write it as cos square theta is 1 minus sine square theta, or even you could write sine square theta equals to 1 minus cos square theta. So all these are different ways of writing the same expression, which is cos square theta plus sine square theta is 1. Or sometimes we even replace 1 with cos square theta plus sine square theta, right? Now you'll also observe one more thing, that if I start with the same expression x square plus y square equals to r square, instead of dividing by r square, I could even divide by x square, correct? What do I get? X square over x square is 1, y over x is tan, so we get tan square theta, and r square over x square is secant square theta. So we get another expression, and this is the second trigonometric Pythagorean identity. Well, just as we did those two, we could even divide x square plus y square equals to r square by y square, right? In that case, x over y is cotangent. We get cot square theta plus 1 equals to cosecant square theta. Do you see that? So we get the third Pythagorean identity. Perfect. So these are very important identities to remember, and always remember that we can write tan theta as a ratio of sine theta and cosine theta. Correct? So that is how all these trigonometric functions or ratios are linked. Correct? So now let's move on and talk about the identities which we learned. So we'll kind of summarize these identities here. So let me summarize. What we learned here is that tan theta is equals to sine theta over cosine theta, right? We also learned that sine square theta plus cos square theta equals to 1. 1 plus tan square theta equals to secant square theta, and 1 plus cot square theta is cosecant square theta, right? So these are your trigonometric identities. We also learn that sine 90 minus theta in degrees, I'm writing, is equals to cos theta. Cos 90 minus theta is equals to sine theta, and tan 90 minus theta equals to cotangent theta, right? So these are very important trigonometric identities which you should remember. Perfect. Now we'll add more as we learn about compound angles. So I'm leaving that part clean at the moment. So I'll leave it separately. Now let's talk about radian measurements. Now when you are using calculus, then in calculus default unit is radian. All angle measurements. Now this is very, very important to understand, right? Now let's try to understand radian as such. If I have a circle, in that circle, I could always relate arc length to the radius and the angle. So if, say, the angle here is given to you as theta, A is the arc length, R is the radius. In that case, we know A equals to R theta. The arc length, that means this length, is equal to product of R and theta. Now, if A equals to R, in that case, what happens? If I write A equals to R, basically, I can write from here, theta is A over R, right? If A equals to R, that means R over R will get 1, right? So theta is A over R, so we can say 1 radian is the angle for which arc length equals radius. Correct? This is important to understand. So if A equals to R, you can substitute and get theta equals to 1 radian. Now you can also appreciate here that theta is a ratio, right? In radians, A over R, same units. So there are no units. So radian is ratio. Basically no units. We write radian for convenience. So if I just write a number, let us say we say that the angle A is equals to, let's say 2.5. Without unit, it is assumed to be radians. Now this is a huge concept to understand. Do you understand that? Okay. Now, from this particular definition that A equals to r theta, we can actually come to know what theta is for one full circle, right? For one full circle, we know circumference is what? Is 2 pi r, right? That is for full circle, what is theta? What is theta? This is what we need to find. In that case, we can again use the same equation, which is A equals to r theta, right? So let me use that. Equation A equals to r theta. Now for full circle, A is 2 pi r, right? So we get 2 pi r equals to r theta. Now clearly r and r cancel. So we get 2 pi is equal to theta. So in radians, full circle means angle of 2 pi radians. Okay. So one thing important in calculus, we always use radians. Second, what we just now found is full circle angle is 2 pi. Correct? Full circle angle is 2 pi. Now, in case you are working in degrees, if you are working in degrees, then what you learned is that the full circle is 360 degrees, correct? So that means the relation between degrees and radians is what? Is 360 degrees equals to 2 pi radians, correct? So that becomes the relation. So what we can, another thing conclude here is that if you have to convert the units, then 2 pi is equals to 360 degrees, or pi is equal to 180 degrees, right? Now this conversion is very, very useful, and we are going to use this conversion a lot. Since you are familiar with degrees, radian might be a new unit for you. So, but use pi equals to 180 degrees for conversion. Very useful, let me write down angles in degrees and radians for you, especially the ones which we are going to use many times. Let me give you a few examples here. So let us say if the angle in, let's just say angle in degrees and in radians. Okay. So we'll try to write down few relations between degrees and radian angle. So if angle in degrees is 0 degrees, in radians again it is 0, we'll use this conversion factor, correct? If I use 180 degrees, I have radian value of pi. Half of 180 is 90 degrees, so it should be pi by 2. And half of 90 is 45 degrees, so it could be pi by 4. Does make sense to you? Is that all right? Perfect. So these are a few easy ways of figuring it out. Now if I give you another angle, which is, let us say, 1/3, I know, forget about the scale kind of thing, right? Let's look into next set now. So if I say pi by 3, it means what? Pi by 3, pi is 180, 1/3 of 180 is 60 degrees. Does it make sense? If I say pi by 6, we are doing the reverse now, right? Divide 180 by 6, what you get is 30 degrees. Does make sense to you? So you could go the reverse way. So you could go the reverse way, kind of like this. Do you see that? In general, if I say you have to convert 72 degrees to radians, what will you do? Well, easy method is 72 is in degrees. You do not want degrees. You want radians. You're going to use this ratio multiply this by something which is radian on the top and degree below. So this factor pi over 180 will always be 1, correct? So if you multiply this by this factor, you're not changing any value. Does make sense to you? So that is how you could do it. And you can simplify this to get the result, dividing both by 6, for example. 6 times 30, right? 6 times 1 is 6 and 2, 12. And further we can divide by 6. 6 times 5 and 6 times 2. So what you get here is equal to 2 pi over 5. So 72 degrees is 2 pi over 5 radians. Does make sense to you? Correct? Now, if I say, let us say 2.5 radians, and if you have to convert to degrees, how will you do it? Well, the easy way here is, you know it is 2.5 radians. You have to multiply by a factor which has radians in the denominator. So we could divide this by pi radian and times it with 180 degrees. Does make sense to you? So that factor is going to give you the result of 2.5 radians into degrees, correct? So let's multiply. So we get 2.5 times 180, which is 450 over pi in degrees. Do you understand? Right? So you could actually get answer in decimals. So we'll do 450 divided by pi to get the answer as 143.24 degrees. Is it okay? So you could convert the radians to degrees by multiplying by a factor of 180 by pi. Correct? So the easy way is, if you have to convert from radians to degrees, in that case, since you have to convert to degrees, the factor is, for this, the factor is degrees on the top, 180 degrees divided by pi. Do you see that? That is what you have to do to your radian value. But in case you want to convert degrees to radians, in that case, what is the factor? If you have to convert degrees to radians, you want radians on the top, so it should be pi over 180 degrees. Does make sense to you? So that becomes the conversion factor for you. Perfect. So this is the conversion factor which you should remember. Now the next thing which we'll talk about is how to sketch angles in radians, right? So how to sketch angles in radians, this is what we'll now discuss. So let me make two kinds of sketches here. We'll now see how to sketch radians, angles in radians. So we sketch angles in radians. From this particular graph, if I'm sketching radians, this is 0, this is pi, we know, that is pi by 2, and pi by 2, 2 pi by 2, 3 pi by 2. Is that okay? You can also call this as 2 pi, 0 or 2 pi, correct? Now, if I do half of this, let's say half of this, then what I get? I get multiples of pi by 4, correct? I get multiples of pi by 4. So this becomes pi by 4, 1 pi by 4. This is 2 pi by 4, 3 pi by 4, 4 pi by 4, 5 pi by 4, 6 pi by 4, 7 pi by 4, and 8 pi by 4. Does it make sense to you? 8 divided by 4 is 2, you get 2 pi, correct? So you get 8 pi by 4. It is so simple. You don't have to think much. Now, let us take another example here. And now we'll sketch pi by 6 angles. Pi by 6. So if I have to do pi by 6, that is to say, here we want 1 pi will be into 6 portions. So starting with 0, I want pi by 6. So basically I want 6 pi by 6. That becomes pi by 6. I have to divide this into 6 equal parts, right? So I have to divide this into 6 equal parts. So 1, 2, 3, 4, 5, 6. Do you see that? Those become the 6 equal parts. So if I draw these lines, one of them is definitely this line, and then 1, 2, 3, 4, 5, 6. And I can extend them, right? So I could have this, 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 and this. Is it okay? So each is pi by 6. So starting with 0, this becomes pi by 6, 2 pi by 6, 3 pi by 6, 4 pi by 6, 5 pi by 6, 6 pi by 6, 7 pi by 6, 8 pi by 6, 9 pi by 6, 10 pi by 6, 11 pi by 6, and 12 pi by 6. Do you see that? So easy. That is how you sketch your angles in radians. Nothing can be simpler than this. I hope that is well taken, correct? Now you'll notice that these lines are pi by 3 apart, right? So the multiples, even multiples, are pi by 3 apart. Do you see that? So these are pi by 3 apart. Correct? You could write them as pi by 3, 2 pi by 3, 3 pi by 3, 4 pi by 3, 5 pi by 3, and 6 pi by 3, which is 2 pi. Do you see that? So you could easily sketch all pi by 4 multiples, pi by 3 multiples, or pi by 6 multiples using the strategy of dividing each quadrant into those many parts. Do you get an idea? So I hope that gives you an idea of what the angle in radian is, how is it related with arc length, that's the beauty, how is it related with degrees, how to convert from radians to degrees and degrees to radians, and how to sketch them if required. Correct? Now onwards, when we talk about solving equations, we'll find angles in radians as we are preparing ourselves for calculus. So with that in mind, let's move forward. Thank you. Now let us review period, amplitude, and phase for a sinusoidal function. So in general, we can write the function f of x as equal to a times sine k x minus p plus q, right? So that is in general the sinusoidal function. From this function, you know a is the amplitude, k is basically gives you the period. So k gives you actually number of cycles in 2 pi, number of cycles in 2 pi, and k also helps you to find what is a period. So period is number of times it is repeated, right? So or the time taken for one particular cycle. So period is time t equals to 2 pi divided by k. Now period is always considered to be positive, and so we take absolute value of k. Is it okay? So when I say time period, we are saying time taken for one cycle. Time for one cycle. Is it okay? So that gives you time period. P is referred to as phase shift. Q is axis, or you can also say at times it also reflects vertical translation. For that matter, P could be referred to as horizontal translation. Is that okay? So that is how we can actually see a particular equation. Now, as an exercise, if I give you a function which is y equals 2, let us say 2 sine of 3x minus, let's say 1 minus half. Now, in that case, I like you to write down the amplitude, time period, and also sketch. So I like you to sketch this particular function, right? It's a sinusoidal function. So let's review how to sketch it. To sketch this, what we will do is we will sketch one cycle, right? So we'll only sketch one cycle. Okay. So to sketch it, what do we start with? Amplitude is 2. So here the amplitude is 2 for us. So that means from the axis is 1. So let's rewrite all these values first and then we will sketch it. Okay. So it'll be a good review. So we know amplitude from here is 2. We know axis is this value of minus half. Now what is the time period? Time period is 2 pi. We are going to do everything in radians now. 2 pi by the k value of 3. So 2 pi by 3 is my time period. Is it okay? Now 2 pi by 3 is time period. And phase shift p is 1 unit right. 1 unit right. Now it becomes kind of tricky at times when we use this value 2 pi by 3. So let's get an idea. What is 2 pi by 3? So 2 times pi, you can use 3.14 or this value, divided by 3 is in decimals 2.01. It is approximately equal to, let's say 2.01. Slightly more than 2. That's what I'm trying to say. Slightly more than 2. So when I do a phase shift of 1, it's kind of slightly more than half of it, half of the time period. Do you get my point? So 1 here really means that it is almost half of it, correct? So that's the whole idea. Okay. So to sketch this, what we should do is we can start with the axis itself. So axis is at minus half. So that is minus half, let us say. Now, the amplitude is 2, so we'll go 2 up and 2 down. So let's say this is 2 down, and let's say 2 up. So if I have to write the values, let me write this as 0.5 with a negative sign. 2 down means negative 2.5, and 2 up means positive 1.5. Is it okay? Now, we'll do it in 2 trials. I mean, we'll actually make 2 sketches, one without phase shift, the other one with phase shift. And this time period will be taken care of. So sine wave starts from here, and one sine wave moves like this. Do you see that? And that time period for us is 2 pi by 3. So it is 2 pi by 3 where it ends. Do you see that? And this point here is 2 pi by 6. Perfect. This point here is, this point here where you get the maximum is half of this. So it is 2 pi by 12. I'm not simplifying. I'm writing this in terms of 2 pi by 12. You could always write pi by 6 here. Is it okay? So that is how we have. The phase shift, as you see, is 1, which is slightly less than, it is almost half of it. Do you see that? So the phase shift is almost this much. So the wave actually starts from here. So the phase shift, which is 1, is almost half of it. So it is kind of here. Do you see slightly before this? So the actual graph starts like this. So it's kind of like this. Do you see this graph? So that becomes the final graph. So the final graph is shown in pink color. So you should have an idea of what this relates to, right? So the time period is approximately 2.01. Phase shift is 1, almost half of it, correct? So that is how you could sketch the function. So I hope that is absolutely clear. Now as an exercise, you can take up another example. Let me call this function f of x is equals to half cos, let's say 2x minus 1 plus 3. Now for this particular function, I like you to sketch the function, write down all these things, right? So before you do that, let me remind, you should actually write this function as cos. Factor out 2, don't forget that, and you get x minus half here, right? And then sketch, otherwise you could make a mistake here. Do you see that? So that is kind of important to understand, and that gives you a good review of working with trigonometric functions, basically model functions, using radians. Now, one cycle normally is 2 pi, so the k value should be written in terms of 2 pi. So I hope that is clear. Okay, so now let's move on. Now let us try to understand how to solve trigonometric equations. We'll take simple equations and we'll take domain of theta to be from 0 to 2 pi, right? So for all our calculations. As soon as I write 2 pi here, it should be clear that we are working in radians, correct? So let's take few equations. Let's say the equation could be sine theta plus 1 equals to 0. We can say cos 2 theta equals to, let's say, 1. And let's say sine square theta equals to, let's say, equals to 1 over 4, right? So let's solve these equations one by one and try to understand the strategy. Now, the very first one given here, sine theta plus 1 equals to 1, basically means sine theta equals to 0. So whenever you have an equation with sine theta equals to 0 or sine theta equals to plus or minus 1, it is a good idea to use the sine curve and find the solution. Sine curve basically is like this, as you know, with a time period of 2 pi, and it has 3 zeros. These are your 3 zeros, and they are at 0, pi, and 2 pi. And therefore, the solution is theta equals to 0, pi, and 2 pi. Perfect. Now, when I say cos 2 theta equals to 1, we're actually working in the domain of theta equals to 0 to 2 pi. But if I say 2 theta, the domain increases, and 2 theta should be between 0 to 4 pi. You just multiply this by 2, and so the domain increases. Now, for cos curve, whenever you're working with 1 or minus 1, the cosine function, you could sketch and get your solution. For cosine function, it starts with 1 and it ends with 1. And it does have period of 2 pi, correct? When you say 1, it means we are actually looking for 2 theta equals to 0, or this is 2 pi. Now, since we have to go forward till 4 pi, you need to understand that we have to take 2 waves, right? So it's kind of like this, as again 1 at 4 pi. So 2 theta equals to 0, 2 pi, and 4 pi are our solutions. So theta in radians will become, you divide them by 2 as 0, pi, and 2 pi. Do you see that? So that becomes the solution for the second equation. The third equation here is Sine square theta equals to 1 over 4. So you can write sine theta as equals to square root of 1 over 4. Whenever you do square root, you should take both plus and minus into consideration. And so we get plus minus half as our result. Now, plus minus half, that reminds you of a special triangle, which is pi by 6, pi by 3, right? So this special triangle where the angle is pi by 3, pi by 6, and the sides are 1, 2 and square root of 3. Since you're looking for plus minus half, you have to look for also all the four quadrants, right? Within 0 to 2 pi, as you know, that all are positive in quadrant 1, sine in 2, cosine in 3, and tan in 4. Now, if you're looking for plus minus half, that means we're looking for a solution which is half, is pi by 6. So we're looking for these solutions. Do you see that? We're looking for these solutions. We are looking for these 4 solutions. All give you plus minus half. How do you get all of them? Well, theta is equals to, for half in the first quadrant, gives you pi by 6. In the next quadrant, it is 1 less than pi by 6 or 5 pi by 6. Now here it is 1 more than pi by 6, 7 pi by 6. Now here it is 1 less than 2 pi, correct, or 12 pi by 6, which gives you 1 less as 11 pi by 6. So you get these 4 solutions. Do you understand? So taking simple equations, that is how you would actually get different solutions. Now let me take few more examples which could be slightly more tricky. Now if I say that, let's get back to this with cosine 2 theta, just as we did here, right? So let's take 2 of sine 2 theta, let's say, equals to 1. How are you going to solve it? Since we are talking about this, we can write this as sine 2 theta equals to half. Now we are talking about 2 theta, not theta. So our domain changes. Our domain will become, for 2 theta, it is going to be between 0 to 2 times 4 pi. Is that okay? And the same thing, same situation. However, we have to go for one more cycle. So in this case, we'll say 2 theta is equal to pi by 6, 5 pi by 6, 7 pi by 6, 11 pi by 6, and then we have to add one more cycle to it. That is kind of important to understand. One more cycle to it. That is to say, you have to add 2 pi to each one of them. Adding 2 pi means 12, right? So 12 plus pi is 13 pi by 6. 12 plus 5 is 17 pi by 6. 12 plus 7 is 19 pi by 6. 12 plus 11 is 23 pi by 6, correct? Now theta is going to be half of these. So if you do half, you get pi by 12, 5 pi by 12, 7 pi by 12, 11 pi by 12, 13 pi by 12, 17 pi by 12, 19 pi by 12, and 23 pi by 12. Do you see a small change which I made in the equation resulted into a huge difference in number of solutions, right? So that is a very, very important part to understand. Now if I give you an equation which is, let's say, cos 2 theta is equals to 3, well, we know that that is not possible, so no solution. So at times for equations, so we see that cos 2 theta equals to 3 has no solution. And now you understand that the range for cos theta is between plus n minus 1, and similarly sine theta value also varies between plus n minus 1, correct? So those are the limits for these functions. It is always less than absolute value of 1. Perfect. Now let us use calculator to find some values in radians for a given equation. So let's take few equations like, let me take one as sine theta equals to 0.25, right? In that case, theta is equals to sine inverse of 0.25. Now we can use calculator to calculate these values. First thing, of course, is you have to change the mode to radians, right? So for us, 4 is radians. And now we will do sine inverse of 0.25. Shift sine inverse 0.25 gives us a value of 0.25268. Let me write this as 27. So that is one of our solutions. As you have seen, sine is actually positive in quadrant 1 and in quadrant 2. So there should be another answer also. The other answer will be theta equals to pi minus whatever you got, which is 0.2527, correct? So we have to find that answer also. So it is pi minus 0.2527, which is equal to 2.888. So you get 2.888. So for sine theta equals to 0.25, you get two solutions. One of them in quadrant 1, 0.2527, the other one in quadrant 2, right? So that is how you can use calculator and find the answers. So let's take one more example. Let's find out the answer for tan theta equals to, let us say, 1.27, right? So I'm taking tan theta as 1.27. I need to find solution between 0 to 2 pi. So tan is positive in quadrant 1 and in 3. Time period for tan is pi. So whatever you get in quadrant 1, you can add pi. Theta equals to tan inverse of 1.27. So that is, we have tan inverse of 1.27 equals to, it gives me 0.9037. That is one value of theta. So let me call this as theta 1. The other value will be pi plus this much, since it is positive in quadrant 3 also. So we can do pi plus 0.9037. Okay, so we'll add pi to this, which gives us 4.0537, correct? So these are two solutions for tan theta equals to 1.27. Anyway, what you understand here is that in calculus, all the calculations should be done using radians, and now you understand how you can find different solutions for an equation in radians. So as an exercise, let me write down this question for you. Let it be sine 2 theta plus 1 equals to let's say 2 over 3, right? Let's say 2 over 3. So find solution for this in the domain theta between 0 to 2 pi. Great. So let this be a question for you. So let's move on and now look into compound angles. The compound angle formulas which are very useful for you are sine A plus B, which could be written as sine A cos B plus cos A sine B, right? And if I have sine A minus B, then there is a minor change in the formula. It is sine A cos B minus cos A sine B. Now from this formula, we can get a lot of related formulas. We could add them, right? So if I add them, what do I get? I get sine A plus B plus sine A minus B as equal to. These two terms cancel, so I get 2 sine A cos B, correct? So that's what we get. Now, in this particular formula, sine A plus B plus sine A plus B equals to 2 sine A sine B. If I substitute, okay, now that is for sine A plus B. We have a similar formula for cosine. We could use cos of A plus B, which is cos A cos B minus sine A sine B. And cos of A minus B is cos A cos B plus sine A sine B. And if you add these two, what do you get? Well, again, the last two terms cancel. And what you get here is cos A plus B plus cos A minus B equals to 2 cos A cos B, right? Now you could have subtracted them also. So if you subtract, you get 2 cos A sine B for sine and minus sine A sine B for cosine. So let me write down what do you get for cos of A plus B minus cos of A minus B. It is important to note when you take away, you get it with the negative sign 2 sine A sine B, right? But if you do the same thing for sine function, which is sine A plus B minus sine of A minus B, so when you do minus, they get subtracted, but you get plus 2 cos A sine B, correct? So these are very important formulas to remember, right? And they are called double angle formulas. Double angle formulas are applied to solve equations where we may have angles like 75 and things like that, 75, 15, since we know the value of 60, right? So, for example, if you have to find what is cos of, let us say, 15 degrees, for example, cos of 15 degrees, right? Now, we really don't know the value of cos of 15 degrees, but we could always write this as cos of 60 degrees minus 45 degrees, correct? I've just taken it in degrees for the time being, but just to explain the concept. So we know cos of 60 minus 40 is, we can apply this formula and we can write this as cos of 60 degrees times cos of 45 degrees, take away sine of 60 degrees, sine of 45 degrees. So in a way, we can find the exact value of such expressions, right? So let's use our special triangles to evaluate this particular value. So I'm just making two triangles, one for 45, which is pi by 4, one for 60 degrees, 1, 2, and square root 3, right? Now, cos of 60 degrees is half. Cos of 45 is 1 over square root 2. Minus sine of 60 degree is square root 3 over 2. And sine of 45 is 1 over square root 2. So now you can take common denominator of 2 square root 2. And what you get here is 1 minus square root 3, right? You may have to rationalize it. That is multiplying both by square root 2. So if you multiply by square root 2, you get 1 minus square root 3 in the numerator. And 2, let me write 2 times square root 2 times square root 2. And finally, you get square root 2 times 1 minus square root 3 divided by 4, right? So that is kind of an application. You can find exact values for angles other than 30, 60, 90. Is it okay? So as an exercise, you can find what is sine of 75 degrees. So let this be a practice question for you based on this particular exercise. Okay. Now let's move on, and now we'll take up double angle formulas. So in double angle formulas, we'll actually again work with the original compound angle formula, which is sine A plus B equals to sine A cos B plus cos A sine B, right? Now if I substitute B as equal to A, both as A, what happens? I get sine of A plus A equals to sine A cos A plus cos A sine A. A plus A is 2A, so I could write this as sine of 2A equals to 2 times sine A cos A. So that's the double angle formula for sine. Similarly, we can find double angle formula for cosine also. Cos A plus B is cos A cos B minus sine A sine B, right? So if I substitute B equals to A, we get cos A plus A equals to cos A minus sine A sine A, right? So cos of 2A is cos square A minus sine square A. Now this is a very interesting and useful result. We use it in so many different ways in trigonometry and in calculus. Let me show you how. If I combine this formula with the result that cos square A plus sine square A equals to 1, then we can write this in different forms. I could replace cos square A, this is A. I could replace cos square A with 1 minus sine square A, correct? So that is to say, we could say cos square A equals to 1 minus sine square A, right? So I could write cos 2A as equal to, replacing cos square A as 1 minus sine square A. We already have minus sine square A here. It gives me 1 minus 2 sine square A. Do you see that? So in a way, we have converted cos into sine. That is a huge application. Similarly, we could write this cos 2A also as replacing sine square A as 1 minus cos square A. We could say cos square A minus 1 minus cos square A. We could write this as 2 cos square A minus 1. Correct? So these are your double angle formulas. Now these double angle formulas can also be written as half angle formulas. Let me show you how. So we have cos 2A equals to cos square A minus sine square A. We have cos 2A as 2 cos square A minus 1, right? So let me use this space here to rewrite these formulas in a different way. So what we have here is cos 2A equals to 2 cos square A minus 1. Now if I replace 2A with theta, so that is to say, if I write this as cos theta, I get here 2 cos square theta by 2 minus 1. Do you see that? Now we can rearrange. So we can write, bringing it here, we can write this as 1 plus cos theta as 2 cos square theta by 2. And then dividing and square rooting, we get 1 plus cos theta divided by 2 with the square root equals to cos theta by 2. Whenever you do square root, you have to write plus and minus. Correct? So we have got the half angle formula. Do you see that? Now the same thing could be done with sine 2a formula also, and this could be actually rearranged and written as sine theta by 2 equals to plus minus square root 1 minus cos theta over 2. So they become half angle formulas for you. You get the idea, right? So this is very useful, and at times you may have to change your equation in one particular ratio, so that helps. So you can convert cos into sine anytime using this particular application. So I hope that part is absolutely clear. Okay, let's move. Now let me summarize most of the trigonometric identities which we have learned so far. Beginning with tan theta, which could be written as sine theta over cos theta, right? And we know the reciprocal angles, which is cosecant theta can be written as 1 over sine theta. Secant theta can be written as 1 over cos theta. Cotangent theta is 1 over tan theta, correct? And then we learn the Pythagorean identities, which is cos square theta plus sine square theta equals to 1. 1 plus tan square theta equals to secant square theta, and 1 plus cotangent square theta equals to cosecant square theta, right? So this is one set of identities which we learn, and then we also learn that cos of pi by 2 minus theta is equal to sine pi by 2. I mean sine theta, and cos, I should write sine of pi by 2 minus theta is equals to cos theta, right? Similarly, tan of pi by 2 minus theta is equal to cotangent theta. All these formulas we get from the triangle, understanding that one of the angles in the triangle, if it is theta for example, this is 90 degrees, correct? So if one of the angles is theta, let me write this time theta here, and then the other angle is 90 minus theta, or you can say is pi by 2 minus theta, right? So this angle is in radians pi by 2. So if you look from this side, the side is opposite. But if you look from the other side, it becomes adjacent, and that is why you get these identities, and these are called co-function identities, right? Then we learned in application of double angle. So we learned that sine 2 theta is 2 sine theta cos theta, correct? And cos 2 theta could be written as cos square theta minus sine square theta. This could also be written as 2 cos square theta minus 1, or 1 minus 2 sine square theta, correct? So that is the double angle. And when we converted them to half angle, we found that sine theta can be written as 1 minus cos, theta by 2, let's do half angles, right? So cos theta by 2, cos theta by 2 can be written as plus minus, of course, right? Now it really depends in which quadrant the angle is, then you have to choose the sign. 1 plus cos theta over 2, and tan theta is their ratio, so tan theta by 2 will be plus minus square root of 1 minus cos theta over 1 plus cos theta, correct? So these few identities help you to solve most of the questions. These Pythagorean identities could be written in different forms. For example, cos square theta could be written as 1 minus sine square theta. And 1 minus sine square theta, you could also write this as 1 plus sine theta times 1 minus sine theta. So I hope you get variety, right? So you get sine square theta could be written as 1 minus cos square theta, which is 1 minus cos theta times 1 plus cos theta. Correct? So you could arrange them in this fashion and use these identities in solving trigonometric equations. Correct? Now let's take up examples of few trigonometric equations. Now let us see how to solve trigonometric equations. We'll actually try to understand a strategy here to solve trigonometric equations. Let me take an example as 1 plus sine theta equals to cos theta. And let us say theta is between 0 to 2 pi. Now in this particular equation, you will notice that we have both types of terms and it becomes really difficult to solve such equations. Strategy is to write in one form, that is either in sine or in cosine. So I'll actually show you two different ways of solving such equations. So we'll do case 1, in which we will square both sides and then solve. So the equation given to us is 1 plus sine theta equals to cosine theta. We'll square both sides, right? So we'll square this side and we'll square this side. Once you square, you actually incorporate errors. So you should check for errors also. So basically, when you square, you need to check result. This is important because minus becomes positive when you square, right? Okay. So let us square and figure it out. We have 1 plus sine square theta plus 2 sine theta as expansion of this plus cos square theta. Now we could write cos square theta as 1 minus sine square theta, right? So we could write this as 1 plus sine square theta plus 2 sine theta equals to 1 minus sine square theta. Now we have a quadratic equation in sine, bringing all the terms together. 1 plus sine square theta plus 2 sine theta minus 1 plus sine square theta equals to 0. 1 and 1 cancel. Sine square theta plus sine square theta is 2 sine square theta. And here we have 2 sine theta equals to 0. 2 sine theta is common. We get, sine theta plus 1. Let me write this as, okay, sine theta plus 1 equals to 0. Now for this equation to be true, sine theta could be equal to 0 or sine theta could be equal to minus 1. So whenever we are looking for sine theta solutions, it is good practice to sketch the sine curve and see when it is 0 or minus 1. So from this graph, you can easily figure out that sine is 0 for the values as theta equals to 0, pi and 2 pi, correct? So 0, pi and 2 pi are your solutions. And theta is minus 1 here. So which is, sine theta is minus 1 for theta equals to 3 pi by 2. So these are the solutions which you get. However, whenever you square, you should check your result whether this equation is being satisfied or not. So if I substitute 0, in this case, what do I get? If I substitute 0, I'm checking the equation 1 plus sine theta equals to cos theta, right? So sine 0 is 0. However, cos 0 is 1, so this is fine. Now when I substitute pi, right? So when I substitute theta equals to pi, in that case I get 1 plus sine pi. Now sine pi is 0, of course, and cos pi is what? Cos pi is minus 1, right? Cos pi is not 0. Let me sketch the graph for cos function also. So for cosine, the graph is kind of like this. So you will notice that in cos function for pi, you get -1. This is -1. So that is not true. And therefore, this result is not valid. So pi is not valid. You get an idea, right? So it is important to check the results. Okay. If you check 2 pi, if you write 2 pi here, cos is 1, and 1 plus sine 2 pi, you get 1, which is cos 2 pi. So this is fine, right? And if you check for 3 pi by 2, then we have 1 plus sine 3 pi by 2. Sine 3 by 2 is minus, and cos 3 pi by 2, so it is 1 pi by 2. 3 pi by 2 is 0, right? So we do get 0, which is okay. So all other values are perfectly fine. So ultimately, the valid answer is, for this equation, theta equals to 0, 2 pi, and 3 pi by 2. Is it okay? Pi does not satisfy this equation, correct? Why you got this answer? Because you squared it. -1 squared is +1. That's why you got that answer, right? Okay. Now that is case 1. You could do like this, but you have to be careful of checking the values. Case 2. In case 2, we will write these terms in terms of half angle, right? So we have the equation 1 plus sine theta equals to cos theta. We know that sine 2 theta could be written as 2 sine theta cos theta, right? So I could replace sine theta by half angle formulas. Similarly, cos 2 theta could be written as, in terms of sine, 1 minus 2 sine squared theta, right? So these values I could write in terms of theta. So what I'm trying to say here is that I could write sine theta as equal to 2 sine theta by 2 cos theta by 2, and I can write cos theta as 1 minus 2 sine squared theta by 2. You get it? So we are going to do this substitution and then solve. So if I do this substitution, I get 1 plus 2 sine theta by 2 cos theta by 2 equals to, instead of cos theta, I'm going to write 1 minus 2 sine squared theta by 2, right? Let's bring the terms together. 1 and 1 cancel. We get 2 sine theta by 2 cos theta by 2 plus 2 sine square theta by 2 equals to 0. Now we can take 2 sine theta by 2 common. So we get cos theta by 2 plus, here we get sine theta by 2 equals to 0. Now either this term sine theta by 2 equals to 0, or this term, which is cos theta by 2 plus sine theta by 2 equals to 0. Both gives us solutions, right? Now, as far as the range is concerned, we are working in theta between 0 to 2 pi. So what happens when it is theta by 2? We have to divide this by 2. So we get 0 to pi. Perfect. Now, for sine theta by 2 to be 0, within this interval, which is between 0 to pi, sine is 0 for theta by 2 equals to 0, or theta by 2 equals to pi. Is it okay? These are the two values for which sine theta by 2 is 0. So that gives us that sine, the theta equals to 2 times 0, which is 0, right? Or theta equals to 2 pi. So we get two solutions, theta equals to 0 and 2 pi, from this condition. Now let us solve the next factor. So if I bring it to one side, then we get what? We get tan, we could write this as sine theta by 2 equals to minus cos theta by 2, or tan theta by 2 equals to minus 1, dividing by cos theta by 2. Perfect. Now when is cos theta by 2 equals to minus 1? Now we are working in the domain for theta by 2, which is basically 0 to pi, right? That domain. So within this domain, when is tan negative? Tan is negative when you are in quadrant 2. So that is the solution we're looking for. And the acute angle is pi by 4. So this angle is 3 pi by 4, right? For which it is minus 1. So we get theta by 2 equals to 3 pi by 4, or theta equals to 3 pi by 2, right? So we get exactly the same answer which we got earlier. So that becomes the next solution, which is theta equals to 3 pi by 2, right? So we get same three solutions which we got last time, but we have adopted two different ways of solving the trigonometric equation. So I hope with this you learn and also recall all the concepts about trigonometry which will be applied in calculus. So the whole idea is to refresh and begin with calculus. So that brings to the end of this particular video. We have learned different techniques of using our trigonometric ratios. We have recalled the formulas, and now I think you're absolutely ready to take on calculus with trigonometry. All the best.